Assalamualaikum warahmatullahi wabarakatuh. Let's continue tutorial for chapter 6. Okay, problem 655. Refrigerant 134A enters the condenser of a residential heat pump at 800 kilopascal. So we have refrigerant 134A enter the condenser. Specifically, we are talking about condenser. And it is basically a heat pump. And this is the value, 800 kilopascal and 35 degrees Celsius. Okay, enters the condenser. And you have the rate also, mass flow rate, 0.018 kilogram per second. And it will leave the condenser at 800 kilopascal as a saturated liquid. So you can see immediately the exit condition is actually at the saturated condition, saturated liquid specifically. So if you recall, saturated liquid X is equals to, the quality X is equals to 0. Okay, that is where it exited. If the compressor consume 1.2 kilowatt, so the work requires is 1.2 kilowatt, okay, power. Determine the COP of the heat pump and the rate of heat absorption from the outside air. All right, I think this will be quite an interesting problem. This is a good description of the refrigeration and heat pump cycle. You have compressor and then condenser, expansion valve, and evaporator. Okay. And specifically, I think the problem describes information about the condenser. And we know that heat pump, then it will extract heat from a cold space and then call that throw out or release heat from the system to the intended space, okay, Q.H, okay, to the already hot area. Okay, let's try to solve this problem. Okay, we have the system already there, but before that, that's as what we have done before. Let's put a diagram of the, what we call that, heat pump. We have a residential, that is our interest, okay, residential. Okay, and that is where we want to supply the heat. So QH will be going there, or QH dot specifically, and we have our heat pump to provide the push the heat to the residential, or also extract the heat from the cold surrounding. Okay, and this is from our outside. Okay. All right, so we take heat from the cold outside and then throw to the residential area, or supply the heat to the residential area. And of course, we know that you require work in this case, that we just indicate work in there. So this is the overall, and the detail of the heat pump, you can see this is the process. So QL is from the outside, okay, and QH to the residential, and it require work to run the compressor, to run the heat pump system. Okay, so the first part, A is to find the COP of the heat pump. We know COP for heat pump, the relation is we are interested in the supplying the hot air to the residential. So yeah, this one should be QH dot divided by the amount of work requires, in this case indicated as W dot in. Okay, so this is the equation that we need to get. We have work dot W in already. We are given this as 1.2 kilowatt, 1.2 kilowatt. We need to find QH dot. QH dot is not given, but we know that QH dot, from this problem, we have a flow there. We are given the mass flow rate. Okay, QH dot is nothing but M dot H2 minus H1. We're talking about enthalpy because we have we call that U plus PV, the flow, workflow there, okay, or flow work rather. Okay, so we have M dot, but we need to find H2 and H1. What we mean by 1 and 2, this is state 1 before entering the condenser, and this will be state 2. So if you can find the enthalpy of 1 and 2, then we can find or we can relate the QH dot. All right, and of course we are given the value, the properties here, so we should be able to find from the tables. All right, so let's go to table. This is refrigerant 134A, so you need to use table A12 and A13. So if we go to, for the first one, okay, at 1, and that may be a bit confusing. Let me erase that. Okay. At 1, so from table A12, let's check the saturated table first. Let's see if I can open the table from here. Yeah, okay, if you refer to the table, the pressure is 800 kilopascal. You can see that 800 kilopascal is here. Okay, this is A12 refrigerant, saturated refrigerant, 800 kilopascal. If you have this, you can see that 800 kilopascal, the saturated temperature is 3131. So let's go back here. So let's put down here. P equals to 800 kilopascal. From the table, T saturated is equals to 31.31 degrees Celsius. But we are given 35 there, which is, we know that saturated temperature is less than the temperature given. So the temperature in the working fluid is higher than the saturated temperature. And we know in that case, therefore, we know that the working fluid is already in the superheated vapor region. Right? So no superheated vapor, then we can go to table. From table A13, then we can use table A13, which is the superheated vapor table. And we know that our properties, P equals to 800 kilopascal, and temperature is equals to 35 degrees Celsius. So let's go to the table. If you go down to the table, let's see if I can go. Yeah. Okay, this is A12. Let's go to A13. A13, we find the table with 800 kilopascal. This is 800 kilopascal. You can check that the saturated table is saturated temperature is 3131. Okay. Unfortunately, we don't have 35 degrees Celsius in the table directly, but we know the saturated value, and we are given the 40 degrees Celsius. So you have to interpolate between these two. You can see saturated, of course, is 3131, and then you have H value 267.29 there. For 40 degree, you have 276.45. So then, as you know, you will have to interpolate. So interpolate. Okay, what you have is the temperature. You have saturated temperature, which is 31.31. This is in degrees Celsius. And you have your property, your state 1 property as 35 degree. And the one in the table also we have 40 there. And we are interested to get the enthalpy H. H from the table is kilojoule per kilogram. For 3131, the H value is 267.29. And of course, we do not know this. Let's call that as H. This is the first state. So H1, okay, something, the one that we want to find out. And for 40, we know that it is 276.45. So if we interpolate this, you know that you have H1 is nothing but equals to, if you do this relation, it is 35 minus 31.31 divided by 40 minus 31.31. Okay, multiply by 276.45 minus 267.29 plus 267.29. Okay, you should be able to get this relation. Okay, and if you calculate this, you'll have H1 equals to 271.24 kilojoule per kilogram. Kilojoule per kilogram. That will be your H1. Okay, interpolating from table A13. All right, so for at 2, you are already given it is in the saturated, and in fact it is saturated liquid value. So immediately you can just simply use table A12. Okay, for the value of P equals to 800 kilopascal, and you know specifically X is equals to 0. The quality is 0, saturated liquid. So if you refer to the table, let's go just quickly just to show the table. We have 800. Okay, so we are interested in finding the saturated liquid. It is just HF then in that case. So 895.47. Do not need to identify the in between or interpolate, because X is equals to 0. So from that, then you know H2 is equals to HF because of saturated liquid condition. And from the table is 95.47, 95.47 kilojoule per kilogram. Okay, that will be your value. So let me go to this here, moving up there. Now we know H1, H2, we also know the mass flow rate. So you can go back to the equation QH. So QH dot is nothing but M dot H2 minus H1, which is equals to M dot is 0.018 kilogram per second, given in the problem there. Okay. H2 is 95.47, 95.47, and then minus H1, which is 271.24, 271.24. The unit is kilojoule per kilogram. Cancel kilogram, so you have kilojoule per second, and your QH dot in this case is nothing but 3.164 kilowatt. 164 kilowatt if you calculate that. Okay, we have that QH value now. Then we can go back to our earlier, the first equation that we are interested to find. Therefore, our COP for heat pump is nothing but QH over W in, which is nothing but 3.164 kilowatt divided by W dot in is 1.2 kilowatt. Same unit there. So if you calculate, then this will be 2.64 value. Okay. This is the coefficient of performance for that condition. Okay, that is the first part. Second part, for B, right? So the rate of heat absorption from the outside air, rate of heat absorption, which is nothing but Q dot L. Okay, so you know that from energy balance, this is we need to find Q dot L. Okay, that's basically the question. The amount of heat we extract from the outside. From energy balance, you can see that there are two energy coming in and one energy going out. So you know that QH dot is equals to QL dot plus W in dot. So QH dot is nothing but equals to QL dot plus W in dot. Since we want to find QL dot, we know already the other two, so you rearrange QL dot is nothing but QH dot plus W. It's not plus, you bring W to the other side, so it should be minus. Okay. Minus W in dot. Okay, just rearrange that. And we have both values. QH dot is already calculated there. Oh, but by the way, I made mistake there. There should be a minus there. Okay. Minus because this is smaller than the other one. What does that minus indicate? It just indicating that you are losing energy or you are losing heat, which is right. We have Q leaving the system, okay, going through the residential. So it is expected. It's okay. You can put also negative there to indicate, but usually then you can take the magnitude that you do not need to put the negative. Negative just indicating that you are losing your energy. So enthalpy outlet is smaller than the inlet enthalpy. All right. So in our case, then we have QH. Still, in this case, you do not take the negative value because it indicated by this direction. When we have this energy balance, you are already taking into account the direction. So QH should be the magnitude 3.164 minus work in is 1.2. And if you do that calculation, then you have the value to be 1.96 kilowatt. So that will be the answer to the second part, the rate of heat absorption. And you can see that 1.96 kilowatt amount of heat is extracted from the outside. And then you are supplying heat to the room in the amount of 3.164 kilowatt, okay, by utilizing work of 1.2 kilowatt, okay, to the compressor. Okay, I think that will be for this problem. Okay, we'll see you again for another tutorial. Okay, Assalamualaikum warahmatullahi wabarakatuh.